Hello, my name is Zhang Puyu. I'm currently doing a program in mathematics with a second major in computer science at the National University of Singapore.
Hi, my name is Wallace and I'm 26 years old this year. I graduated from NUS with 2 degrees, one in chemical engineering and one in mathematics. My research interests are quite diverse, but I plan to work at the intersection between engineering and applied mathematics. I'm currently a research engineer in the Department of Chemical and Biomolecular Engineering at NUS. I'm currently working on control theory and machine learning applications in control theory, as well as a little bit of theoretical machine learning. I hope to embark on my PhD this year.
Hi, I'm Zoe. I'm 19 this year and I just graduated from Raffles Institution. In RI, the subjects that I took were physics, further math and econs, and I hope to pursue data science in a US university.
Hi, my name is Thang Pang Ern and I am an alumnus of Nanyang Junior College, where I spent 2 years pursuing my A-levels. I'm a prospective undergraduate student and I hope to major in mathematics at the university.
I'm Joseph. I'm a student from Malaysia, currently pursuing a double degree in mathematics and computer science. I've been in Singapore since 2018 when I came here through the ASEAN scholarship.
Hi, I'm Mr. Leong, and I'm a teacher at Nanyang Junior College. And I've been in this school for the past close to 33 years. I started teaching in 1990, June 25th. And ever since I've been teaching both mathematics as well as further mathematics. And also, I'm also currently teaching history mathematics.
Well, like many others who are interested in math, my story with mathematics started with games. I think I was one of the fortunate kids in my generation whose parents did not fill my childhood with early education tuition classes, but instead they gave me absolute liberty to play all kinds of games. Among all the games that I have played, I was particularly intrigued by jigsaw puzzles and building blocks, and soon I became quite good at them. As far as I can remember, I can build complex stuff like skyscrapers and tanks with Lego on my own at the age of 4. When I got my first laptop during my primary school days, my interest in building blocks soon got me kind of addicted to the game Minecraft. And as compared to physical Lego bricks, I enjoy Minecraft even more because as a sandbox game, it allows me even greater degree of freedom in building. And when I play it, I get a sense of being a creator in the world I have set up. As my building skills progress with the game, I soon realized that by placing simple shapes in certain particular ways, I can build more and more complex structures.
Ever since I was a kid, my mom realized that I displayed a higher level of proficiency in math than the other kids around me. So what my mom would do is that usually she would buy me workbooks that are like around 2 grades ahead of me, and I would just try them out. But it was really only until like when I was around 14 years old when I actually started out Math Olympiad in school. During Math Olympiad, I'm very grateful that I had a great teacher. His name is Xie Guojun Lao Shi, who he really taught me and he really inspired me throughout the entire journey. So he's this around a 60 plus 70-year-old teacher who's really enthusiastic about math. And I could still remember that when he was teaching the Math Olympiad class, like he would get so excited about a particular topic and he would actually jump on his feet. So it was really inspiring and exciting to have a teacher like this, and he always entertained challenging questions that were oftentimes beyond the syllabus. So through his guidance and alongside some self-studying, I've actually managed to have a good grasp of elementary calculus by the time I was 15 years old.
My whole life, I've had a keen interest towards math, and I have to accredit my parents for this. So from young, before math was being formally taught in school, my parents would expose me to math in daily life. For example, if I want to get a snack, my parents would make me calculate the change correctly, and I would be the ones writing their checks, so I would have to get my number placings right. Naturally, it led to me having the habit for discovering the association between numbers and my daily life. So for example, when I first learned prime factorization in secondary 1, I would actually do that to all the car plate numbers that I see on the road. And I believe that developing this association and finding math between the things I see in daily life and what I learn is what makes math so enjoyable for me. Besides that, school and teachers also played a huge part in developing my interest towards math. So everybody would learn the same formulas, but my school would give me the opportunity to apply these into math modeling projects. So for instance, when we were learning about quadratic functions and parabolas, one of the projects that I did was to track the motion of a ball using a tracker and develop a quadratic equation and find the optimal distance to shoot the ball from. So when we were learning about interest rates, another math modeling project that I did was to model how long it would take to pay off a university bank loan. And in this project, we took account into real-life factors such as income earned from a part-time job and the cost of living.
I remember in primary school, math was one of my worst subjects. And in primary 5, I failed one subject, and that subject was mathematics. So I am definitely not talented in math. Okay, I'm definitely not a child prodigy. Definitely not. In fact, my best subject when I was in primary school was probably art, and I used to draw cartoons and those days, Bruce Lee comics, those Hong Kong, comics was very popular, and I like to draw those things with commentaries in Chinese. When I was in primary 6, I started working hard, and I started to do much better in math. Yeah, I still remember my mark in primary 6 was 86 out of 100. So that was quite an achievement for me. Yeah, considering the fact that I was failing maths all the time.
I've always been fascinated by puzzles and problem solving ever since I was a young boy, around 5 or 6 years old. My mum played an instrumental role because she was the one who introduced them to me, and she joined me in playing all sorts of puzzles, such as building blocks, and this one especially. I call this the soccer balls puzzle, and it still stuns me till today because it seems like a simple toy where you connect the blocks, but you ensure that the soccer balls do not come into contact with each other. And even though the puzzle was seemingly simple, I actually never once solved it independently unless I referred to the solution. Nevertheless, the joy of playing puzzles was my first step towards liking mathematics because it built up my problem-solving skills. From primary school to junior college, I had the fortune to be under the guidance of great mathematics teachers. My mathematics teacher from primary 3 to primary 6, for instance, Mrs. Wendy Yap, she was an exceptionally brilliant mathematics teacher. She was the one who ingrained the essence of proofs, and she told us to, understand concepts rather than to memorize and regurgitate them. She also told us many fascinating mathematical ideas that were way beyond the curriculum, such as, elementary results in number theory and the Fibonacci sequence and how it is related to the golden ratio. It was around this period where I started to gain serious interest in mathematics because I was so fascinated by these seemingly advanced ideas and that they could be explained to a primary school student in a very succinct and entertaining manner. I am very grateful to have fantastic mathematics teachers, namely Mr. Leong Chong Ming and Dr. Heng Chang Wee. They were inspirational, and they challenged us with crazy questions and gave us insights as to what studying mathematics was like at a university level, which was indeed rigorous. And it involved one to seriously delve into the realms of mathematical proof, and I loved that kind of rigor.
Back in my high school days, I was much more into physics than mathematics. So one day I was reading Griffiths, Electrodynamics by Griffiths, and there was a whole bunch of math inside. So there was like multivariable calculus, there was Fourier series, there was PDEs, and I was really getting stuck because I was unable to grasp all these intense mathematical ideas. And so I decided that, if I were to study more mathematics, I might be able to overcome some intellectual hurdles that I will encounter in the near future.
Subsequently, my exploration with shapes in Minecraft got me interested in geometry, which is one of the first reasons why I love math class during school. Unlike many other mathematically inclined students, I remained quite indifferent towards algebra for many years, and this only changed when I was 14. At the start of year 2 in my junior middle school days, I learned about the Cartesian plane coordinates and functions, which was a big shock to me, because all of a sudden I realized that all the sophisticated shapes, structures and buildings that I have created in games are merely a visual representation of the numerical relationship between variables behind those shapes, which really is the core that governs the appearance of all the shapes we see. The lesson gave me a sense of enlightenment because it feels anti-intuitive and disoriented when you realize that all materials existing in this world with a tangible shape and everything that we can touch and see in the world we live in is actually derived from abstract concepts, numbers, logic, theorems, and mathematical operations. These are things without any tangible forms, yet they create and govern all the concrete objects and motions in the physical world we live in. At that moment of enlightenment, mathematics appeared to me as a magical tool that creates this world out of an invisible void. And it was from that day onwards that I became truly captured by the beauty of mathematics.
When I went to Sec 3 and Sec 4, I had a very good teacher, very patient teacher, Mrs. Koh Sui Yin, and she was my E and A math teacher. In fact, I went on to study on my own topics that my teacher hasn't taught. Like for example, integration. Yeah, so because I was curious to know, I couldn't wait for teacher to teach, and I just read the textbook and I understood. When I went to junior college, well, I did double math. I did Max B and further Max B, and I had very good teachers. Just to name a few, Dr. Yap Siok Phui. She was Miss Yap at that time, but later on she got a PhD, and we call her Dr. Yap. She was with me for the 2 years of my JC life, and she taught us analysis, group algebraic structure, mechanics even. And I must also thank Mr. Yo Yi Sing. He was the HOD of mathematics, and he also taught us mechanics, and I must thank my teachers for inspiring us. That's my experience in school, from primary school to junior college, and I have many teachers to thank. Yeah, certainly without them I wouldn't be what I am now today.
Around like the same time when I entered Math Olympiad at the age around like 13, 14, I also came across a really interesting TV show called Numbers, in which a mathematician, he actually applied mathematics to help his brother in the FBI to solve crimes. So of course it's a TV show, and a lot of the mathematics in there used were exaggerated, but it was actually quite interesting because after I saw the show and I learned about the mathematics used in there, like such as like a graph theory used in like trying to detect cycles and detect money laundering, or like using like graph theory to find like the roots, find like the source of an epidemic. So things like this was really interesting. I actually started looking into these mathematical ideas online, and I realized that hey, they're actually not fictional, they're actually real. So that was really cool, and it really inspired me to delve more deeply into mathematics.
Fast forward to my junior college days, I took up a very unconventional subject combination which comprised physics, further math, math and geography. And also when I was in year 2, I took up an additional subject on top of all my current subjects, which was H3 mathematics. So you can see that my junior college life pretty much revolves around mathematics.
In hindsight, how I started doing mathematics seriously in university was purely a coincidence. So back in year 1, I was trying to look for some difficult courses to do. Like, I really just wanted to YOLO and push myself to the limits. So that's when I decided to try out the SPM. So the SPM in NUS is known as the Special Program in Math, and it's basically you take the normal math modules and then you kind of amp it up and then it becomes like something a bit harder. So my first math module in NUS was Mathematical Analysis 1S, which was MA2108S. I believe it's still coded that way. And it was a really intense struggle for me because I was not used to the level of difficulty and the level of rigor that people expected of me. But I think I became a much better thinker at the end, and I was really happy about it. And also, I really like the challenge of doing math, and I really like the things that I can apply math to. So that's why I decided that, I really like math and I should just do a second degree in math anyway.
I'm most intrigued by how math has so much relation to the things we see around us every day, and that's why I've been exploring the field of statistics. So everybody can be given the same data set, but everybody has a different method of analysing it. How then do we best determine which is the best way or what gives the most accurate answer? This ties back to my interest in data science, where a lot of these are being automated using codes and computer programming. And using codes and computer programming gives us an unbiased way of finding out what is the so-called best method. And through this, I've been exploring the use of data science through various projects and in various industries as well.
Back in 2020, I participated in the ST Yao High School Science Award with two of my friends in my junior college, Fan Bo and Ruojin, where we chose the Gauss circle problem as our topic of research. This problem asked for the number of lattice points, that is, points with integer coordinates, present in a circle with radius r, centered at the origin. For example, such a circle with radius 2 has an area of 12.57 and contains 13 lattice points. Though the problem was seemingly innocent, while researching towards a solution, my team soon realized that it was far more complicated and challenging than we expected, because it encompasses lots of higher level ideas at the university level, such as the Fourier transform. Nevertheless, it was indeed a great opportunity to conduct such a research, as we learned a lot throughout the process. My team and I were grateful to explore into such areas of mathematics, which are beyond the junior college syllabus.
Graph theory is also a field that I'm greatly interested in, mainly because it has a lot of practical applications in the real world, and it's very much linked to the algorithms that we design in computer science. So a very good example is that your GPS, it oftentimes tries to find the shortest route between 2 points, or two cities, or 2 locations. So the way it does that is that what we're doing is that we're modeling these cities and the roads. The cities, we model them as nodes. That's essentially what we model them in graph theory. And for the roads, we model them as edges. So this is the idea where we convert things into a network, into a graph, and through that we study this type of graphs, and from there we can derive algorithms such as Dijkstra's shortest path algorithms to help us find an efficient solution that would give us the shortest path between 2 points while not having to consider all the possible points that we have to go through. And another thing that's very interesting in terms of this type of graph theory algorithms is also known as psychodetection. And this could be very useful if we think about things like money laundering, and we want to detect whether someone's moving account from one account to another and to maybe 10 other accounts before moving the money back to himself. So these are things that we can develop an algorithm for to detect within bank transactions and things like these. So advancements in graph theories can lead to breakthroughs and better developments and improvements in state-of-the-art pathfinding algorithms, and even prove certain hard limits on currently unsolved problems that include the traveling salesman problem.
So my first project was a research on image geolocation, and that means to be able to identify the location when an image was taken based on the image itself. So if you think about it, things like the Eiffel Tower or the Golden Gate Bridge, these are things that are relatively easy to identify because they have distinctive landmarks. But if you think about something different, like a beach, the beaches all around the world look roughly similar. And so it would be quite difficult to identify specifically which beach it was taken at. So to solve this problem, I considered the use of other cues like EXIF data and metadata taken from the images itself.
In fact, the subject itself really caught my interest. I remember very vividly when I was in junior college, first 3 months. In those days, we have, we can enroll in the junior college during the first 3 months using the prelim results. All right, and those days, the result will be released after March. So I went to Hwa Chong, and I remember very vividly that Miss Yap, at the time Miss Yap, she taught us mathematical induction. Just the beauty of the argument itself really mesmerized me. I was really literally mesmerized by the beauty of the argument. It's basically to prove some statement based on the natural numbers. You have to prove that that statement holds for every natural number. And we know, right, the set of natural numbers is infinite. How are we going to possibly sub every single natural number to verify the truth of the statement? But mathematical induction allows us to do just that. You just have to prove it true for the first case, and then we assume an arbitrary case and prove that it's true for the next case. And based on the logic behind, we can conclude without a shade of doubt that the statement holds for all natural numbers. And that was beautiful to me. I remember I was just thinking about it, for the next few days after Ms. Yap taught. At that time also, I started recording some beautiful math on notebooks. So I have my notebooks. So I would record down some beautiful math that I come across, and I would solve those problems.
So I'm a personal believer that mathematics can be applied in many different ways and unexpected ways. During my Europe, I was tasked to, take a whole bunch of crystal images, like a time series of crystal images, and each image has many crystals inside. And I was tasked to come up with an algorithm. So this algorithm was meant to measure the number of crystals, and 2, the length of every crystal in the image. And this was not an easy task because the current algorithm to do this is known as the radon transform. And the radon transform is, for one, it's kind of slow when we try to put the images in, and it also gave very noisy outputs. So these outputs were basically useless because they had too much noise. And another thing is that crystals, they have non-negligible width. So they have these lines, but they also have non-negligible width. But in the event where there's zero width, then the algorithm will work perfectly. But because we have width, so now it's noisy. So now this output was really noisy, and we had to do something about this because we really wanted to know the length of the crystals in every image. And so my main insight was that I could use the divide and conquer paradigm. It's kind of like a thinking paradigm for algorithms. And basically I combined this with the radon transform to get a much better result using the radon transform. And what I did was just focus on regions of the image where there were crystals. And in itself, the radon transform is a mathematical transform, which is really interesting, and you need some level of mathematics to understand it. And I was really surprised that I could apply mathematics to these kinds of unique situations where I did not expect myself to apply any form of mathematics at all. And so I was really happy about that project, and in the end I managed to become one of the authors in a publication in Crystal Growth and Design for that paper, and I was really happy about that.
Machine learning is an area that I'm very interested in as well, and it's also a branch of artificial intelligence. So in today's society, machine learning, artificial intelligence, these are buzzwords. These are hype words that people are very excited about. But oftentimes people don't really know what's going on behind them. Now, in fact, what's actually going on behind them is just clever optimization techniques. And in mathematics, we call this technique gradient descent, and through which we are able to minimize and reduce the costs, or also known as the error of the predictions made by the machines. Now, after we've applied such techniques, there are other nuances that we need to take care about. And the first thing to take care about is how do we strike a balance between creating a network, a model that is too simple or too complex? So the issue at hand is that if we have a model that is way too simple, then the model would fail to unravel any underlying pattern in the data that it's trying to learn from. However, if we have a model that is way too complex, then the model would just take in everything, and it will just memorize everything, and towards the end, it will just try to regurgitate out the answers. So that would not be ideal as well. As such, in the area of machine learning, oftentimes we're trying to strike a balance and learn how to find a perfect balance in this situation.
In my machine learning model, I applied the mathematical concept of weighting. Some factors were determined to be more important than others, and therefore they would have a greater impact on the results. So my machine learning model was tested on a set of 3,000 actual images, and in the end, the accuracy of image geolocation proved to increase by 30%. So my next project was particularly meaningful for its social purposes. In Philippines, a lot of housing appraisals are done manually, and so this causes high levels of biases. So to help reduce this, what I did was try to automate the housing appraisal process. And to do this, I collected historical data on the attributes of houses, such as the size, the land area, the number of bathrooms. And so what I did was then to analyze how the importance of this to property prices. From then on, I was able to build a machine learning model that analyzes all these factors to make a prediction of the price of a new property listing. And so the use of this helps to eliminate the biases in the manual housing appraisal process.
In the year, 1994, there was a big thing that happened in the mathematical community. Andrew Wiles proved Fermat's last theorem. Okay, so Fermat's last theorem was proposed by Pierre de Fermat in the 1600s. Okay, so he conjectured that a to the power n plus b to the power n is equal to c to the power n, where a, b, c are natural numbers. He conjectured that this equation has no solution if n is larger than 2. We know that if n is equal to 2, there are infinite solutions, and we call these Pythagorean triplets. But once n gets to 3 or more, there will be no solution. So it's a very simple problem, but has a very profound solution. So actually Andrew Wiles, he proved it. Okay, he spent 8 long years in isolation and harnessing the latest mathematics, the 20th century mathematics. He was able to finally prove it. The interesting thing is that Fermat claimed that he had a proof, but of course certainly his proof would only use elementary mathematics, because in the 1600s the mathematics was not so advanced. So one thing that really doubt whether Fermat had a simpler proof, but he never left behind a proof. But he did prove the case when n is 4 by using his technique of infinite descent. But Andrew Wiles actually proved it for n greater than or equal to 3. So that was a big thing. It came out in the papers, Straits Times. He finally nailed the problem and gave it a final blow. So that was an amazing story, and I would use that story to actually inspire my students to be persevering in doing mathematics and never give up.
My current interest in mathematics is number theory. So number theory is simply the study of the properties of integers, and it is a course that is taken fairly late into university. And I feel that it carries a great amount of elegance. As what the great German mathematician Gauss once said, mathematics is the queen of the sciences, and number theory is the queen of mathematics. I completely agree with this quote. Number theory goes far beyond the elementary properties of the study of integers, such as divisibility tests, which would be covered in a primary school math Olympiad setting. So at a slightly higher level, I look into things like Diophantine equations, which are questions which seek integer solutions to an equation. So I guess the most famous and maybe the most basic Diophantine equation out there would be Pythagoras' theorem. So Pythagoras' theorem is an equation in x, y, and z, and it is quite clear that the triple x, y, z is equal to 3, 4, 5. This triple satisfies the equation. And it is the most fundamental one, and there are other solutions too. And of course, there are other Diophantine equations out there other than Pythagoras' theorem, such as Pell's equation, and the most remarkable, or I would say the most notorious one, Fermat's last theorem.
So during my JC years, I was part of the Nanyang Research Program, known as NRP, and it was hosted by the Nanyang Technological University. So during this program, I wrote a paper in which I attempted to fill in the gaps of the proof of the Johnson-Lindström's lemma, so these gaps are things like the things that the authors would deem as trivial, but they are not that trivial to non-experts in the field. So I'll try to fill in the gaps, and it's actually pretty interesting because it's related to fields that I'm very interested in, such as linear algebra and probability. So what is the Johnson-Lindström's lemma? Well, this is a result that tells us that we can find a projection, a mapping from higher dimensional space to lower dimensional space while still preserving the distance between any two points to a certain extent. Here is an animation of the preservation of distance in action when the points are being projected down to a lower dimensional space. This is very fascinating because intuitively we feel like it's very unlikely for us to be able to preserve these points when we project these points downwards to a lower dimension. But however, this Johnson-Lindström's lemma it tells us that we can actually find a projection like this with a probability that is larger than 0. In other words, it tells us that it is indeed possible for such a mapping to exist, and it can be found. So it was also during this time, when I was bridging the gaps of the proof, that I learned about techniques in probability that we can use to give a lower bound of the probability of events occurring. And through that, we're able to prove this result.
I started teaching in the year 1990, June 25th. And since then, I've seen many batches of students. There are students who have left a deep impression in my mind. They impress me because they are very passionate about mathematics, and they are able to see mathematics from a very matured standpoint, right? Because a lot of students see mathematics as just a subject that they have to pass or to do well, or they see mathematics as a means to an end. They need to do maths in order to get into some courses, you know. There's nothing wrong with that, okay? But there are very few students who look at mathematics differently, who look at mathematics not just as a subject or as a means to an end, but as an end itself. Very few students study mathematics for its own sake, just because it is beautiful, because it is worth pursuing for its own sake, for its intrinsic value. Very few students see maths that way, because to me mathematics is a way of thinking. All right, to be educated mathematically, to be numerate, okay, or to be well educated mathematically means we can look at the world from a pair of mathematical lens. Okay, we look at the world differently. I love interacting with students. Okay, so in my past many years of teaching, I have enjoyed my interaction with students, particularly the further max students and the special paper students, and now the history students. So I always enjoy having mathematical conversation with able students who are able to talk mathematics. And I must mention, I particularly enjoy teaching the batch from 2020 to 2021. That batch of further max students and history students, they were very lively, and we had a lot of conversations.
As of now, I'm leaning more towards analytic number theory, which combines concepts from calculus and complex numbers. And so, analogous to the atoms in chemistry, prime numbers are like the building blocks of mathematics. They're actually quite mysterious because they are pretty simple. Like, you can list down the prime numbers 2, 3, 5, 7, 11, and so on, but you can't sort of find an explicit formula that talks about the prime numbers. So like you can't simply say that, oh, I want to generate the 600,000th prime. I don't think there's a way to do it as of now. And also another kind of question that we will ask is that due to the fact that primes become more sparsely distributed as we go along the number line, we would ask, is there a formula that talks about the number of primes less than or equal to a given number with an explicit expression? So the much celebrated prime number theorem in analytic number theory, it talks about the distribution of prime numbers. And fortunately, although we don't have an explicit formula for the number of primes less than or equal to a given number, we do have an approximation for it. So I find it pretty interesting that analytic number theory, or number theory in general, has loads of interesting stuff to offer.
I like playing computer games, and I especially love strategy games. I've played many strategy games, including Civilization, Humankind, Europa Universalis 4, Victoria 3, Crusader Kings 3, and Stellaris. Among all those games, I have noticed a common issue that negatively affects players' experience. For example, poorly balanced buffs can make the player unbeatable too fast, and the late stage game becomes boring. And as game mechanics get updated, they could get overpowered and break the original strength balance between different factions in these strategy games. Also, certain game stats could get inflated, and this will greatly reduce the level of immersiveness when playing the game. As I discovered these issues with strategy game design, I soon realized that mathematics, such as data modeling and optimization, can provide important solutions in the field of game development.
Aside from mathematics, I was also a competitive bowler for a very long time. I think this was a really integral part of my development because it taught me really important things like having a fighting spirit, having patience, and also being able to persevere in the face of hardship. And I think these are really important things when doing math. I also really enjoy learning Korean, and this was inspired by my interest in K-pop. When I was suffering from intellectual burnout, especially when studying mathematics, I listened to a lot of TWICE and BTS. I felt that it would be an extreme waste if I didn't understand any of the lyrics and what they were talking about, so I decided to learn Korean. In hindsight, that was really one of the best things I ever did because there are many parallelisms between Korean and machine learning. So for example, when you're trying to learn a concept, you might think that, oh, you just need to learn positive examples. But also, if you want to learn the concept well, you need to have many negative examples. You need to have both the positive examples and the negative examples combined together to generate a good data set for your concept. So this was one thing that I learned in Korean that maybe math doesn't really have a lot of, but definitely important for Korean. And yeah, I made many Korean friends along the way, and I'm quite happy about that.
Was last year. Yes, last year I started offering this course on algebraic structure for interested students during the NY Rich. Now, NY Rich is actually a program in the school where students are free to participate in any course run by teachers or even students. Yeah, so they are free to learn anything, right? So I capitalize on this platform to offer a course on algebraic structure. Basically, it's a group theory, okay? And I got students on board, they were interested, and I conducted this course over a span of 8 lessons, each about 1 hour. Yeah, and the reception was, I believe, good, and students enjoyed it. Yeah. It's not offered in A level, not in further max. Yeah. So this course on abstract algebra or algebraic structure is actually now offered in undergraduate mathematics. And this year I started this course on mechanics, one of my favorite subjects, and I used to teach mechanics in further max the earlier years. And I also thoroughly enjoy myself and my interaction with the students. Yeah. So I hope to continue to use this platform to teach courses, mathematics courses that will interest students. When I first came to Nanyang in 1990, I realized that there was no math society. There was a computing society, but no math society. So I believe the math society, if there was any, was subsumed under the computing society. So when I came, I wanted to start a math society. So I started a math society in 1990, and I got all the further math students to be members. So they became automatic members. Yeah, and I still remember the president was Lee Liang Chai. I still remember his name, Lee Liang Chai. Went on to do computer science. Yeah. So what we did in the math society was we conducted some talks. I gave some talks. I remember one of the talks I gave was on the Buffon needles problem, which is basically is a Monte Carlo technique, and based on it's a probability problem, and using that I was able to estimate the value of pi by throwing needles randomly onto a grid, a certain grid with horizontal lines. Yeah. So I also invited NUS professor, and one of whom was Professor Leong Chong Ming, came and gave a talk, and also Professor Tan Gian Lee from the School of Computing, who is incidentally he's now the Dean of the School of Computing. Yeah. So we also run a competition in the college. So we have annual maths competition, and we also come up with maths bulletin. Annual maths bulletin. Right. So these were the things that we did when we first started off. And then it died a natural death after about 10 years. And then only quite recently, the last 5 years, we resurrected the maths society, and we made, it is actually a student-initiated program. So again, we got all the further maths students to be automatic members of this maths society. They actually do some research in mathematics and share with the people, the members. Yeah.
I got into photography and videography when I was in secondary 2. I actually see connections between the photographs that I take and the mathematical concepts that I know. So this is because I see relations between the aesthetic beauty in photos that I take and the geometric features that I learn from mathematics. So there's actually one favorite way that I like when I compose photographs, and that is other than the rule of thirds, I sort of like to create this perspective or depth effect. In a way, it gives the viewer some sort of idea how far he or she is away from the foreground and background, and it also creates this very nice blurry effect, for which in photographic terms is known as a shallow depth of field. So the foreground is blurred and the background is in focus.
In my free time, I like to play some sports with my friends that include like table tennis, and I also like to game with my friends. So sometimes we just hang out on a Minecraft server or just some other games, and I also like to read in my free time as well.
My pursuit of mathematics did not stop after I graduated from university. I continued to read math on my own, and I got interested in differential geometry, got a few books on that, and even Galois theory. And so I'm still reading math on my own in my free time. So that is one of my hobbies. In fact, I had the opportunity, that was the year 2011. 2011, it was about almost 20 years after I started teaching. I went back to school. I joined NTU NIE, and I did a master program in mathematics, and thoroughly enjoyed it. 2.5 years, part-time, on a part-time basis. Yeah. So I remember I had to go over to NTU, after a lesson, twice a week, and the lesson was from 6 to 9, and I never fell asleep, even once. Yeah. So I really enjoyed the math, going back to school, to graduate school, okay, and learning those mathematics. In fact, my lecturer, one of my supervisor, Prof. Zhao Dongsheng, one time he asked me, you must be very tired when you come, right? Because after one long day of work. You must be very tired, and you have to come here to sit through math lecture and lessons. You must be very tired. In fact, and then my reply to him was this. I said, I come here to recharge. And he laughed. I never saw him laugh that much. He was a very quiet guy, very, a man of few words, but he laughed. And they asked me, am I going to do my PhD in mathematics? So, well, I'm open to that.
Other than math, I also like to spend time in the kitchen whipping up my creations. I used to aspire to be a professor in mathematics, but recently I have developed a new prospect for my future career pathway in the game design industry. In particular, I wish to become a game balance designer who deals with balancing character stats and gameplay mechanics.
In the future, I'm looking at fields like that often revolve around big data, and in this particular case, it will be machine learning as a branch of artificial intelligence. So I would like to be looking into different ways to build models and to train the models so that we can have the machine to learn in a more human-like manner, in a more meaningful manner.
Looking back, I have absolutely no regrets. Doing mathematics actually made me a much better person, and you start to realize how little you actually know the more you know. I also met many creative people who will turn out to be my good friends in the end. I think that doing mathematics can help you get a better intuition on how to solve problems in life in general. I hope to become a prof someday, but the statistics are not in my favor. So if that doesn't work out, I hope to start my new YouTube channel, either that or just try to be a teacher in some way, or join a hedge fund where I think my mathematics skills might come in handy.
So these are some examples of how I've been putting data to good use in society. And I hope that this gives you some insight as to how you can use data in your everyday lives. To be able to turn data into information and then information into insights, that is my aspiration, and I hope that you will embark on this journey with me.
Mathematics is my life. I really can't pass a day without pondering over it because it exudes so much beauty in all sorts of areas. It feels great to do mathematics and to share my love for it with my friends. And well, I hope to become a mathematician one day and to continue inspiring people to have aspiration in mathematics just as how my teachers have done so.
My advice to students who are studying mathematics, okay? I hope you will learn mathematics not just as a subject or as a requirement for some courses, but I hope that you will look at mathematics as an end in itself. Learning maths as an end in itself rather than a means to an end. Because mathematics is truth and beauty. And I remember I attended a public lecture in 1986 by Sir Michael Atiyah. Sir Michael Atiyah was a well-known, world-famous mathematician in superstring theory. And he said this statement, which I still remember now. The year was 1986. Okay? Until now, I could still remember what he said. He said this: if you ask me to choose truth and beauty of mathematics, I would choose beauty. Yeah. So mathematics has to be beautiful. Has to be beautiful. Yeah. And currently, one of the unsolved problems in mathematics is called the Riemann hypothesis. It's still unsolved. It's still a conjecture. But many mathematicians believe that it has to be true because it has to be beautiful. If it's not true, it's not beautiful. Okay? So, so beauty is the yardstick of what is good mathematics. Yeah. So, so I want to encourage you, okay, to love the subject. Okay, mathematics is really worth pursuing, right? And you know, I think mathematics can help us to appreciate the hidden laws of nature, right? So many laws in nature will continue to lay hidden, but mathematics is what expresses all these laws. Yeah. So there are still many beautiful laws to be discovered, okay, with mathematics. Yeah. So enjoy your learning of mathematics. Yeah. Thank you.